So for now, without any further ado, I would like to give the floor to our honorable professor from the University of Technology in Sydney. And it's going to take us through a vast domain and of the evolutionary computation techniques, artificial intelligence. So I'm going to leave it up to him to to give us the most newest insights. So a virtual applause, and we give the floor to Professor Amir Gandomi.
Hello, everybody at Computing Conference, and thanks to the organizer for having me at this event. This is Amir Gandomi. I'm a professor of data science at Faculty of Engineering and IT at University of Technology, Sydney. Now it's a flourishing era of data science, big data, machine learning, and these are among the hottest topics these days. And my presentation is also about an evolutionary machine learning techniques called genetic programming. Actually, evolutionary computation has so many different applications in optimization and also data analytics, but this presentation only focused on data analytics part. So outlines of these features are categorized in three different sections. So from evolutionary data analytics, I mean genetic programming, which is an evolutionary approach which does machine learning. And after introducing the concept and some philosophy behind genetic programming, I will discuss some case studies. And finally, I will talk about an approach I proposed called Multiestate genetic programming for data analytics and its application for big data analytics. In real-world studies, we usually involve data like experimental data, numerical data, etc., and usually have a table like this. And data mining intends to extract information and knowledge from these data. This computational process of discovering patterns in data sets, usually large-scale data sets, is called data mining. Data mining can simply be classified in two different classes. When we aim to predicting the future, it's called modeling, like regression and classification. And when we intend to explaining the past, it's called exploration, such as feature selection or descriptive statistics. Generally, data mining modeling tools classified in two different categories. Statistics methods like regression and AI methods like artificial neural network, fuzzy logic, deep learning, support vector machine, and also genetic programming. And in this study, I focus on these techniques, genetic programming. Generally, in data mining, we need to make two main decisions, or I should better say two big selections, selecting the features and selecting the models. Before even going for feature selection, we usually do some pre-processing like mapping, feature engineering, or normalization. And then we try to find optimum number of variables, like what you can see here. So this process is feature selection, which means feature gives us the best accuracy. And then we have model selection. There are hundreds of different models out there. And first, we should narrow down our models based on the problem. And then, by testing different methods, we can find the best model or selecting the best model. For example, in this case, for medical imaging, we apply different techniques, and we eventually find XGBoost is the very, very good techniques for this problem and has the highest accuracy. But I should say genetic programming is a technique which does both these selections inherently via evolution. It selects the best features and also starts modeling from scratch without any predefined structures. So, speaking of evolution, we should go back to evolution philosophy, which came from Rumi, and Rumi, also known as Maulana. He was a 13th century Persian poet and philosopher from Greater Khorasan. And Rumi believed in evolution in some sort of Darwinian sense, which you can find it in his poems. Like از جمادی مردم و نامی شدم و از نما مردم ز حیوان سر زدم مردم از حیوانی و آدم شدم, which means I died as a mineral and become a plant, and I died as plant and rose to animal. I died as animals and I was man. And in 18th century, actually, Charles Darwin proposed the theory of evolution, the breakthrough, yes? And actually in his book called On the Origin of Species, and following the principles of Darwinian natural selection, genetic programming creates programs in order to find relationship between inputs and output. And usually an evolutionary process has an iterative form like this, you can see. And each iteration is called generation. And as you can see, in each iteration, we have evolutionary mechanisms like selection, crossover, and mutation. Genetic programs can be represented using this traditional form called tree structure. You can see in this tree we have mathematical operators, variables, or even constant numbers. And now evolutionary mechanisms like crossover and mutation can happen between these trees. But why genetic programming? First, I should say genetic programming doesn't need predefined structure. Unlike most machine learning techniques methods like ANN, regression, or fuzzy logic, which you need to provide a model structure like network information, number of layers, number of neurons, activation function, etc. But in GP, it starts from scratch and try to build a model structure via evolution. Also, GP doesn't need pre-processing like some other methods that use normalization or standardization, and it can model behavior without any prior assumption, which is also important. And compared to other machine learning models, genetic programming models are relatively short and simple. And as I briefly mentioned, genetic programming can select the features via evolution. And finally, I should say, GP already applied to several complex real-world problems. So it's a reliable technique, it's not a new technique. Actually, I should say, one of the companies that first used genetic programming is NASA. They use genetic programming for designing communication antennas for ST5 mission in 2006, and you can find it in their paper in 2008. And let's start with the first case study, which is a complex structure called self-centering concentrically braced frame system. So we apply genetic programming for modeling the response of this structure. But why this structure is complex? You can see beside the basic frame element, This structure has, for example, these PT bars which connect the roof to the ground. It has a lateral load-bearing element which connects this adjacent gravity column to the frame column and makes this structure behavior very complex. Here you can see idealized SCCBF behavior under lateral loading. The blue lines are post-tensioning bar between roof and ground. And let's see the behavior using force displacement curve. Under a low level of lateral load, it has the elastic deformation of the SCCBF system, which is similar to the conventional system. But under higher level of lateral force, like wind or earthquake, the overturning moment becomes large enough for one SCCBF column to decompress and uplifting from the base. After the lateral displacement of the frame is dominated by rigid body rotation of the SCCBF, which is a rocking response. The post-tensioning bar elongates from the uplift of the frame until this post-tensioning bar yields, and as you can see here. This softening behavior intends to limit forces, so post-tensioning bar yield before the members. So you can see it as a very complex behavior. So we try to study real design, which is an office building designed for a stiff soil site at LA, California. And this is the structure that is studied. And 3 elevation was used in our design: 4-story, 6-story, and 8-story buildings. And 4 parameters used in this design: 2 geometrical parameters, bay height and building height, and 2 mechanical parameters: coefficient of friction and yield stress of members. And you can see the design matrix here. Okay, so we designed 75 different SCCBF systems, and we applied 50 different earthquake records to each of these systems. And what we want to predict using genetic programming is the peak roof drift of these structures during earthquake. And as you can see, this is one of the examples. This is the peak roof drift of one structure under Manjil earthquake. You can see the graph is very stochastic, and the problem seems very difficult. But the results of genetic programming was really promising. For finding the mean of the response, you can see high correlation and low coefficient of variation. And again, for standard deviation, again, low coefficient of variation and high correlation, close to 1. And I should say, for this complex structure, one design procedure proposed by CEO in 2005 at University of Lehigh. They proposed mu-RT procedure, and they try to find these 3 parameters, and each of these parameters has a very complex process. So with this process, we found this point for design of the structures. And we did some experiment, and then we find this point. And then we used our genetic programming model, and you can see it's very close to experimental point. The other advantage of genetic programming is that it's a population-based method. Unlike most machine learning methods, which are trajectory-based methods, this genetic programming works with a population of solutions. So now, in the era of parallel processing, distributed system, cloud computing, we can take advantage of those and run. For big problem, we usually use parallelized genetic program. So the second case study here is when we want to predict the response of a specific earthquake applied to the structure, which makes the problem much harder because earthquake has several specific features which calls intensity measures. I listed some of the intensity measures here, you can see. But when I saw actually the literature, I found more than 30 different intensity measures. So this problem is very high dimension, and I needed to select some of these features. So first, let's go how I did the analysis. I applied 30 earthquake in dB level and 140 earthquake I borrowed from this project. So in total, 170 earthquake applied to each of these structures. And using genetic programming, I want to predict the response of each of these earthquakes. So first, for selecting the features, the simplest way probably is looking at the correlation coefficient, yes? But the problem of correlation coefficient is it's only find really a linear relationship between two sets of data. So I try to replace some part of correlation coefficient equation with GP equation, as you can see here. For example, GP here, GP here. So now this modified correlation coefficient is called evolutionary correlation coefficient. And we found it very promising for this highly nonlinear problem. For example, you can see in this column, this is the correlation coefficient. And in the next column here, I presented the evolutionary correlation coefficient, which I modified using genetic programming. And then in the next column, you can see the improvement in percentage. In some cases, the improvement is huge. So after applying evolutionary correlation coefficient, I selected the best three or highest three correlated features with the output. So then I try to build a model, and one strategy that is very popular in genetic programming is using multi-objective strategy, which means finding a trade-off between accuracy, this y-axis, and also complexity, this x-axis. So I sorted all these solutions and come up with these Pareto front solutions. And eventually, I selected this model as a model which has a trade-off between complexity and accuracy. So these are the final model. If I use a single objective strategy and only I want to maximize the accuracy, this is the equation, and this is the equation using multi-objective strategy. And you can see the accuracy of this single and multi-objective strategy are very close, both close to 0.97 correlation coefficient. And the results are very good, which means they have a very high correlation coefficient, or a correlation coefficient close to 1. The next case study that also was provided a very interesting result for us was predicting concrete creep. First, I should say concrete is a very complex material, and also creep in the concrete is a very difficult problem. So we tried to use genetic programming for building this model, and actually here we coupled linear regression with genetic programming. You can see these are the linear structures, and these are 3 genes using genetic programming. And these are the 3 genes, gene 1, gene 2, and gene 3, which has very simple structures. And let's compare the results with what presented in the literature. So we can, the GC model is what we proposed, and 3 other models presented here. Boson model, which use 10 variable, SEPFIB model, which use 5 variable, and GL2000 model, which use 6 variables. And you can see in terms of correlation coefficient, we got the highest correlation coefficient, and we also find lowest error, which presented in this column. And in terms of other metrics, we still beat the other methods in almost all cases. Okay, let me turn on the light before starting the new case. Hold on. So before starting the next case study, I should say in real world, we usually try to use forward analysis for designing system. Like, for example, we have the input for the system, and we have a design system, and it gives us the output. But in inverse analysis, we have inputs of the system, and we have the output of the system, but we don't know the system prompted. And this problem usually happens when we design a system, and after some time it defected or some damage happened in the system. So we want to find out what's the new system prompters. So one of the strategies that proposed by Professor Gabushi at UIUC is actually this is proposed for finding constitutive material models of any unknown materials. So they try to run 2 different, actually 2 parallel finite element model, one force control and one displacement control, and based on that they develop a data set, and then they train an ANN model. And this cycle happen in each iteration of finite element. But what I've found is, okay, if we have an unknown material and then we develop a neural network model, it's very hard to work with a neural network model because it's usually complex, it's usually black box, it's very hard to take derivative from the system, and therefore it limits its application. So I tried to use the same framework, but only replace neural network with genetic programming. So after replacing neural network with genetic programming, I could simply translate this tree structure to a simple mathematical formula. And now I have a mathematical equation that I can use it as a user-defined equation. I can use it as a user-defined material, and it has far more application. So I define a case study, this cantilever truss, 2 force applied at the end of this truss, and this is the force displacement curve of the system under these 2 concentrated loads. And this is the results by using Professor Gabushi, actually by using ANN. You can see the ANN model is very close to a reference model. So I used linear genetic programming. This is the program. I translated to mathematical formula and got the results. And this is the results of genetic programming for predicting this stress strain curve. So I got back to the software that I use for design. This was the Abacus software. You can see the response of the reference model. And now I used genetic programming in the Abacus software as a user-defined material. And you can see the distribution and even the values for the stresses are very close for these two models. I also saw some other cases like soil modeling and aortic modeling using genetic programming, and you can see in both cases for soil modeling and aortic modeling, we got very good results. And beside these engineering cases, we applied genetic programming in several different areas. For example, for time series analysis of COVID in India, we applied genetic programming and we got a very good result. You can see two of the plots. Then we had some prediction for the next 10 days using genetic programming for number of confirmed cases and prediction for number of test cases. So beside accurate modeling, we could have some prediction for future trends of the time series. And recently we published another paper for predicting COVID-19 in 15 most affected countries, which for sure it includes UK. And you can see, again, we could model these time series and also predict some of the future days using genetic programming. And now finally, the method I proposed called multi-state genetic programming. So what I did in this method is decomposing problem for each variable, which means first I use variable 1 for modeling, then second variable, and so on up to the last variable, and then another function for modeling interaction between variables. So this is the simple structure of multi-state genetic programming, and the rest shows how we come up with each function and how we do each steps in this modeling. And this is one of the case studies we presented in original paper. We tried to model one of the difficult problems called in engineering called soil liquefaction modeling, which means when soil liquefies. So some people already work on this problem, and we also applied several well-known genetic programming for modeling this problem. MEP, GEP, and LGP, these are, I can say, the three most popular genetic programming in engineering. You can see the accuracy of each of these models. And now with multi-state genetic programming, we got 97% accuracy, even without considering interaction between variables. And with considering interaction between variables, we found a very, very high accuracy for these problems. And on the left hand side, you can see the equations we obtained at each stage. 6 stage for 6 variables, and the last stage, or the stage 7, for modeling interaction between variables. And we also tested this model for big data analysis, because now we decompose this multidimensional problem to several one-dimensional problems. It can be very effective for big data analysis. we showed a case study in this paper, and you can see the results in terms of generation and number of errors. It far more quickly reached to the much lower error values. And I should first thank you for listening to my presentation. As I mentioned at the beginning, evolutionary computation has so many applications, and actually at UTS we are doing several different evolutionary computation studies. You can see our lab, our studies. We have several open positions for PhD and postdocs and visiting scholars. And feel free to contact me if you have any question regarding evolutionary computation and genetic programming in particular. I hope it excites you to use genetic programming as a data analytics tool. It has a special, as I briefly explained, it has some special features and can be very effective for real-world problems. And I should thank you all for listening to my presentation. This is my email address, and feel free to contact me if you have any further questions. Thank you.
Thank you so much, Professor, for everything you've given already in this talk, which was very detailed and very specific and very interesting. And we have some also specific questions, so I hope that you will be able to stay with us for a little bit and to answer those questions. A question came in from Syed Muhatasim Abbas Bokhari. Considering the stochastic nature of the technique, how many runs should be made to attain enough confidence on results of genetic programming, specifically in the case when it is very computationally expensive to calculate the fitness?
Actually, this is a very good question. I should say there is no restricted rules for number of runs, but that's what we suggest. It should be enough run to get some meaningful statistics out of it. If you have a big data, for sure you cannot run genetic programming several times. So based on your budget, maybe 5 times, 10 times, or if it's not a very large scale problem, at least 25. And if you have the resources, that's what we usually do. At least 25 if we have the resources, and if it's a very simple problem, sometimes we can go to 50 or 100. But there's no strict rule. So these are usually a rule of thumb.
So a very good question, as you also put out. Thank you so much for this question. I have another one from Alcides Bernardo Telo. What would be the key point, excuse me, in deciding whether to use genetic algorithms or not to use it? Would you narrate something about the search space?
Thanks, very, very good question. So first, this is not a genetic algorithm, this is genetic programming. So genetic algorithm uses for pure optimization, for example, find for some values for some variables. But genetic programming is also looks for a structure of the problem, which means a very bigger search space. And you rightly mentioned what's the search space of this method. So this, I can say, this search space for this method is very huge, and somehow you can say unlimited. So because what any structure you have, you can slightly change it, add something on top of it, or play with the structure. So structure-wise, you don't have search space limit, and it's a very big problem. But particularly when you have a data set. For example, if you want to find an explicit model, if you want to find a mathematical model, or your data set it's not very huge and you can run your algorithm multiple times, genetic programming can converge to models via evolution. And this is the beauty of the techniques. You don't constrain it. You don't say, okay, you should work with this network and only find the weights of these networks, or you should work with this nonlinear structure or this linear structure. You don't say anything, and genetic programming try to find this structure during its iteration or generation by itself. So if you have a problem that you look for a explicit mathematical formula, simple formula, or you really have a time to find exact model for a big problem, you can use genetic programming. Hello? Okay, sure. It seems we lost the host temporarily, so let's wait to see when Lars show up, and I would be around for questions. And even after this presentation, feel free to contact me. You have my email on the screen, and we really like to see if you're doing data analytics or optimization, how we can improve this process using evolutionary computation.
Amir, there is, this is from the production studio. There is one more question that has come in. I won't put myself on screen, but there is one more question that's come in that says, did you experience to any point of some form of non-convergence on some specific type of data? And if yes, what was the reason? That's from Emmanuel Megabo.
Okay, so let me repeat one question that we received. It says, have you ever maybe trapped in some local minima and couldn't converge using genetic programming? And what would be the solution? Actually, this is a very, very good question. First, I should say these problems has global optimum. So there is no universal way of finding a global optimum, because we don't have the mathematical equation or something like this for the problem. I should say it's happened. Most of the time, we don't know what's the global optimum is. So when you run and you, for example, cannot find the global optimum, or you can say a reasonable accuracy using genetic programming or any other machine learning techniques, you can do several things. For example, you can go back to your pre-processing, play with your pre-processing, or you can do some feature engineering, which actually change your search space landscape, which also helps a lot in convergence of machine learning in general, and also genetic programming. So I should say genetic programming in general has less potential to trap in local minima, because it has a very vast search space, but it happened, and there are several steps in machine learning that we can do to avoid trapping in local minima during the learning.
Here now, there is one more question. Sorry, there's a couple more questions that have come in. The first is from Nitin Kumar. It says, what is the future of evolutionary algorithms in robotics?
I'm not really an expert in robotics, but there are several problems that I've seen people try to look at using evolutionary computation. For example, if you have a robot structure, you lost one of the element of that robot. This evolutionary computation could be a one way of adapting this new robot or new system to the environment. Yes, because for example, genetic programming or evolutionary computation can also look for structures. Yes, this could be one of the very good application of evolutionary computation in robotics. And for sure, wherever machine learning works in robotics, we can use genetic programming as well. But as I said, when we don't know the structure in robotics, we can try to find it out using genetic programming. The other things could be finding underlying behavior of robots using genetic programming. Again, this is another structural problem, and genetic programming could be a very good candidate to solve that problem.
Okay, there is another question that's coming from Saeed, which says, is Pareto front optimization based on fitness 2?
Pareto optimization front using fitness 2? I cannot understand. I only have one slide, and I can go back to that one and explain what Pareto front means. Okay, let me again share my slides. So this is the Pareto front. So we don't have fitness 2. We have accuracy as a one objective, as you can see in y-axis, and complexity as another objective on x-axis. So when we run the model during the training, we use multi-objective strategy or Pareto front, as you correctly pointed out, for selecting the best model. And also at the end, we created a pool of models, and then we try to sort them out using non-dominated sorting, and then finding the final Pareto front, and then using selection strategy, we can select the final model. I hope I could answer your question, because I really don't know exactly what did you ask, but I hope these explanations are enough.
Thank you so much for your time and picking your brain. We would have loved to have you with us so everybody could stand up and applaud to you, but now it's just me. Thank you. Thank you so much for being with us, Professor Gandomi.
Thanks so much for having me. And yeah, this is a new format, and we all should be adjusted to it, at least for the next few months. Okay, have a wonderful day, and hope you enjoy the rest of the conference. Bye-bye.
Thank you so much. Bye-bye.